A major characteristic of snapshots is that they're pointer based and they're said to be space efficient. This basically tells us that they don't consume a ton of space on day one. When you initially create a snapshot, it consumes little or no space, and then it only consumes space as and when changes are made to the associated source volume. And the more data that changes in the source volume, the more space that the snap consumes. And the reason that snaps don't consume space until changes are made to the source volume is because snaps are pointer based. And pointer based means that instead of the snapshot containing a copy of the data that's in the source volume, it's just a set of pointers that point read requests back to the source volume. Now I appreciate that this might be a bit confusing if it's new to you, so we'll walk through how this works. Let's start out with our source volume, and we represent this as a series of blocks, sometimes called extents when used in the context of snapshots. In our example, we can see 7 blocks or 7 extents, each with data in them. Now let's take a snapshot of this volume. As we can see, the extents that comprise the snapshot are empty. They don't contain any data. What they do contain, though, is pointers. Pointers back to the extents that make up the source volume. Great, but how does this all work? Well, let's say that this snapshot is a read-write snapshot and that we've mounted it on a host so that the host can read and write to it. If the host that this snapshot is mounted on issues a read request, let's say to block 3 of the snapshot, the pointer in block 3 automatically and unbeknown to the host redirects that read request back to block 3 in the source volume, meaning that the read request will return the value of 3069. And that's how pointers work. But a couple of important points about pointers, and I hope you like what I did there. First of all, pointers barely consume any space at all. In fact, they're often structures held in memory on the host or the array that the snapshot's created on, so they consume way less space than the data that they point to, making them more space efficient than taking a full block for block copy of a volume. And the second point about pointers, there we go again, is that they allow snapshots to be instantly available. Meaning, if you take a snap of a volume at 1 minute and 3 seconds past 5, the snapshot will be available to use at 1 minute and 3 seconds past 5, or maybe a second or two later, but pretty much instantly available. But how do these pointers work when data changes in the source volume? Let's take a look and find out. We'll start by reminding ourselves that snaps are point-in-time copies, meaning that the data in the snap represents the source volume at an exact point in time, the point in time that the snap was taken. Let's look at our source volume again. Now, at 10:40 AM, we take a snapshot of this volume, and as we just learned, this snap is pointer based. And for the record, to help us later, we've added a string of numbers to the left of the broken clock image on the slide. We'll use this later in the lesson to remind ourselves of the contents of the source volume at the time that the snap was taken. Basically, the contents of the source volume as it is now. Anyway, so what happens when data changes in our source volume after we've taken the snap at 10:40 AM? Surely those pointers will then be referring back to data that wasn't part of the source volume at the time the snap was taken. So in effect our snap won't be an accurate copy of how the volume was when the snap was taken anymore. So, what the system does is any time an update is made to the source volume, before actually updating the contents of the source volume, the system makes a copy of the original contents to the snap volume. Let's take a look at it in action. Let's say that since our snapshot was taken, a host issues a write command to update the contents of block 1 in our source volume. But before updating the contents of block 1 in the source volume, the system copies the original contents, in our example this is 0362, to the snap volume, and there it goes. And after and only after the original contents are copied to the snap volume, can block 1 in the source volume be updated with new data, as it is right there. Now, let's assume an update comes in for block 4 as well. Again, before updating the contents of block 4 in the source volume, the original contents are first copied to the snap volume, and then, and only then, is the block in the source volume updated. And this is what we were referring to earlier when we said that snapshot volumes only consume space as and when changes are made to the source volume. So if your source volume is subject to a high rate of change, then any snaps associated with it will quickly consume space. But on the other hand, if the change rate on your source volume is low, all associated snaps will remain very space efficient. And before moving on, let's prove to ourselves how this combination of pointers and copied blocks ensures that we have an exact copy of how our source volume was at 10:40 AM. To do this, we'll read all of the blocks in the snapshot that are shown on the slide. That's blocks 1 through 7, and we'll compare them to our string of numbers that we kept to the left of the clock image. Remember that string that we put there earlier to remind ourselves of the contents of the source volume at the time we took the snap? Okay, so a read of block 1 in the snap volume gives us a value of 0362, which matches the contents of block 1 in our source volume at the time we took the snap. Then a read of block 2 in the snap hits a pointer, and we're redirected back to block 2 in the source volume, which gives us 5833. Again, this is the value that was present in the snap at 10:40 AM. The same thing happens for block 3, and again, the value is what we expect. Block 4 though, it's not a pointer anymore, and the snapshot holds a value of 2214. And checking this against our string of numbers to the left of the broken clock image, we see that this is indeed the value that was present in block 4 of the source volume at 10:40 AM. So we're good there. And then blocks 5, 6 and 7 all hit pointers back to the source volume, each yielding the value that was present at the time that the snapshot was taken. So, through a system of pointers and copied blocks, our snapshot is true to its word, and it can return to us the contents of the source volume exactly as they were at 10:40 AM when we took the snap. And that is how copy on write snapshots, often referred to cow snapshots, work. Now that we know how snapshot technologies work, let's shift our attention to clones.